Hello students, welcome to the class of digital signal processing. We were continuing with our discrete Fourier transform, its properties. We have done several properties: linearity, time reversal, time shifting, periodicity, and circular time shift and circular frequency shift and conjugations. So now today we will be doing the multiplication and convolution. Thereafter we have correlation and Parseval's theorem. So since multiplication and convolution will be a bit longer, so let's first do this two in this lecture. So our today's work is to do, first one is going to be multiplication. Multiplication property of DFT, okay? So the multiplication property says that if you multiply two signals in the time domain, say x1n and x2n, if you are multiplying these two signals, this one is having individual DFT as x1k, and this one is having the individual DFT as x2k. When you multiply them and take the DFT of this full thing, means you are taking the DFT of x1n into x2n, that is going to be the convolution in the frequency domain. Means in the frequency domain, it is going to be the convolution of the DFTs, the individual DFTs, that is x1k convoluted with x2k. So this is the property that we are going to prove today. So for this part, what we need to do is we have to, again, we have to start with the left-hand side or the x1n into x2n itself, but we will again use the IDFT property also over here. So first let's get started. That is our proof. So in the proof, the first thing that we have to write here is DFT of x1n into x2n, DFT of x1n into x2n. Write the formula for this. The formula for this is going to be n equals to 0 to n minus 1, capital N minus 1, x1n, I will take this inside this bracket, x1n into x2n. And this has to be multiplied with e to the power of minus j2 pi k small n by capital N. After this, we will take the IDFT of this one. So here you will write, let us take this one as equation 1. Now we will take IDFT of x1n. The IDFT of x1n is going to be 1 by a. Here the summation will be going from k equals to 0 to capital N minus 1, x1k e to the power j2 pi k n by n. Right? Here it is plus because it is IDFT. Now this I take as equation 2 and I put the value of 2 in 1. So putting 2 in 1, what we will get is n equals to 0 to n minus 1, capital N minus 1. And here we will be putting 1 by n, k equals to 0 to capital N minus 1, x1k e to the power j2 pi k n by capital N. And then we will write x2n e to the power minus j2 pi k n by n. Fine. Now for just to distinguish this k and this k, these two k's, just to distinguish it, we are going to take it this k differently. Let us see. Let this k, let k equals m. Fine. Now, so we will rewrite it, and also at the same time we are going to rearrange it. So what we are going to do is this 1 by n, firstly we are going to take it out. Then we'll write n is equals to 0 to n minus 1. Since this k we are going to change to m, that's why here instead of k equals to 0 to n minus 1, I will write small m is equals to 0 to n minus 1, x1m e to the power j2 pi mn by capital N. Then we have x2n e to the power minus j2 pi k n by n. Fine. So we have to always remember the final destination. So in order to go to that point, what we know that this should be transformed to a x2k. That if we get it, we are done, right? So what we are going to do now is we will change the order of this summation. So for changing the order of this summation, here we are going to write 1 by n. This is just the outside part. Then m equals to 0 to n minus 1. Let this x1m be here. Fine. Let this x1m be here, and the rest of the portion inside the small n with this n equals to 0 to n minus 1. So what do we have? x2n we have. Next we have e to the power plus j2 pi m into n by n into e to the power minus j2 pi k into n by n. Now this part you see, this part is what? 1 by n, just rewrite this part and then we will check what is happening at the other end. x1m. Now this portion, if you see, if you club this together, so j2 pi n by n is going to be the same thing. What is my focus is that I have to make it in the DFT format. So x2n I will write, I will take e to the power minus j2 pi by capital N here, and small n also I will take. The rest of the thing, what is the formula of the DFT? Whenever we write e to the power minus j2 pi k n by n. So in the place of n, here we are going, in the place of k, we are having over here k minus m, right? Now this k minus m is basically going to become, this is basically the DFT for x2, right? K minus m modulo with n. Fine. Now this is over here going to be 1 by n. M is equals to 0 to n minus 1 x1m into x2k minus m. So what is this? If you remember the property of convolution, circular convolution, if simple convolution, if you see, that time we are multiplying after shifting. So this, if I take as our main variable, this variable is time reversed and then shifted by k. So this is basically what? This is convolution. But since we are doing modulo with n, that means we are doing circular convolution here. So this is basically 1 by n, and then it's going to be x1k convoluted with x2k. So going once again through this derivation, what we had to do initially was that we had to prove that if we multiply the signal in the time domain, it will result in the convolution in the frequency domain. So multiplication in time domain results in convolution in frequency domain. This we had to prove. So we started with the multiplied signal, taking the DFT of this multiplied signal. So one of these signal I will write in the IDFT format because that will give me x1k. Here you see, you want this x1k and x2k. So somehow you have to think to bring this x1k. So here what we think of is taking out the IDFT. Once you write the IDFT of x1n, you have this x1k. After that, the things that follow is basically the changing of the order of summation. So this k over here, x1k e to the power j2 pi k n by n. So this k and this k was matching. So that's why we changed this k to m. Thereafter, we are just making it 1 by n, this is a constant thing, so we kept it outside. And finally, the m part, that is the other variable m, that we will move it outside. And this full thing over here, is clubbed together, x2n e to the power j2 pi mn by n and e to minus j2 pi kn by n. If you write this, it is going to become x2 k minus n. This is the discrete Fourier transform. This is the DFT of x2n minus n. Right? This is the DFT of x2n minus n. So it has been shifted. Now you are writing this as x2 k minus n. So this way, we are arriving at this point where you have the summation over here with this variable which we had introduced, small m. Now this variable small m is basically the variable which has been time reversed and then it has been shifted. So time reversed, shifted, and then finally we are having a summation sign also. So basically this whole thing is convolution. And since it is being done on a finite set of values, so that is that n, so we call it circular convolution. So now we have seen that if we multiply in the time domain, then it results in convolution in frequency domain. This we saw in other transforms also. Now the next step that we are going to do is we are going to do the reverse of this. That is the convolution in the time domain, which will result in multiplication in the frequency domain. Okay, so what we are going to do is convolution, circular convolution. So all the things over here, circular time shape, circular frequency shape, circular convolution. Why? Because we are dealing with a finite length signal and then we are shifting it or whatever we are doing it on this length of capital N only. Now here they say that the DFT of the circular convolution of two sequences is equal to the product of their DFTs. So individual DFTs. So what we will be doing here is we will first write the statement. The statement says that the DFT of x1n convoluted with x2n results in multiplication of their individual DFT. So how we write the statement for this? If DFT of x1n is x1k, if DFT of x2n is x2k, then DFT of x1n circularly convolved with x2n gives me multiplication of the individual DFT x1k into x2k. In order to prove this, start in the same manner. Start from here. So it will go from n equals to 0 to capital N minus 1, x1n circularly convolved with x2n. This is my signal actually, and this is going to be that we have to do the discrete Fourier transform of this. So e to the power minus j2 pi kn by n. Now here again, the same thing is going to happen. That is, you have to write the inverse DFT. Okay. So in this case, what we do is basically it's better to start from this side. If you start from this side, that is x1k, the inverse DTFT of this, that will be much easier. So let's do it in this manner. So here you have to start in this manner. We'll start with the ID from the right-hand side. So let's get started from the right-hand side. So what we are going to do is x1k into x2k. We'll start with that. Okay. We'll take out what? IDFT. IDFT of x1k into x2k. How to write this? So we will take that we have the DFT inverse we have to take out, right? So we will write it simply 1 by n, k equals to 0 to n minus 1. We will take this full thing as single signal. So x1k into x2k e to the power j2 pi k n by n. Now next what we do is we'll write the DFTs over here. So n minus 1. Now for this x1k, I will write n equals to 0 to n minus 1. x1n e to the power minus j2 pi k n by n. Again for this one also I'll write the same thing. N is equals to 0 to n minus 1. x2n e to the power minus j2 pi k n by n. Means I wrote the DFT of x1k and x2k. And the whole thing is multiplied with e to the power plus j2 pi k n by n. Now what we need to do is, we need to basically change this first so that we are not confused every time. So there are so many same values and same variables actually. So we need to change this part actually. So 1 by n, k equals to 0 to n minus 1. Let it be as it is. This small n, change it to m. M equals to 0 to n minus 1. x1m e to the power minus j2 pi k m by n. This one tended to p. So p equals to 0 to n minus 1. x2p. So n is equal to p and n is equal to m. That we have done here just for distinguishing. P by n. And this is e to the power j2 pi k n by n. Now, this portion, this one and this one, we will keep it. The rest of the things, that is, what here we are going to do is this portion and this portion. Summation m equals to 0 to n minus 1 x1m 1 by n. Then over here, p equals to 0 to n minus 1 x2p, we wrote together. Here we will start with k equals to 0 to capital N minus 1. So what are we left with? E to the power minus j. So here only the n thing is, k thing is changing. So 2 pi by n, we write it here. Now k, we take it common. Now if you take this k as common, you are left with plus m, plus p and minus n. So m plus p minus n. It is small n. So m plus p minus n. Now very carefully watch at this. This is, I'll write with a different color here. This portion over here, it is what? M plus e to the power minus j2 pi k by n, m plus p minus n. If I take this m plus p minus n, if I take this simple thing, you can also write this as in this manner. K equals to 0 to n minus 1 e to the power j2 pi k by capital N, and then just the signs will change, n minus m minus p. Now, if I take this n minus m minus p as some integral multiple of qn of n, so integral multiple of n. Capital N. So what is going to happen is that we can write this further as k equals to 0 to capital N minus 1 e to the power j 2 pi k q into capital N by capital N. Fine. Now we can just cancel over this capital N's. So we are left with k equals to 0 to N minus 1 e to the power j 2 pi q whole to the power k. Since k is changing, this whole thing is constant, only k is changing. Now q was an integer. Since q is integer, so this full thing is equal to 1. So this k equals to 0 to N minus 1, 1 to the power k. Now this is going to become equal to what? You are doing it how many times? 0 to N minus 1 means you are adding 1 N times. So the answer is going to be N itself. Now this value we will put over here in this part. So in this part, what we were having was 1 by N, and this full thing is becoming N. So basically M equals to 0 to capital N minus 1, x1M. MP is equal to 0 to N minus 1, x2P. And the whole thing is multiplied with just a N. Now see, this was given to us as P and this one was M. Now if I want to convert it into one thing itself, first of all, we will cancel this part. Now if I write it, then I can write it as M equals to 0 to capital N minus 1, x1N. And this one, if I try to write it in the same manner, then what can I write it as? Means if I want to make this thing M is equals to 0 to N minus 1. So my N minus M minus P is equal to Qn. So I will write it x2 N minus M minus Qn. Means in the place of P over here you see, I am writing N minus M minus Qn. So this, how does it help? Here you had M, here you had M. This to M is becoming common. This small n is for the basic signal itself, and this Qn is going to make it shift. So how we write it again is M equals to 0 to capital N minus 1 is fine. This is x1M. Now, again, if you write it, M equals to 0 to N minus 1. Since x2, fine, you can write it as N minus M, just a shifting with modulo of N. So this 2 will be becoming basically what? This is the convolution portion, right? So x1M, these two are the same summations. So we will take it 1. Once only, N is equals to 0 to N minus 1, x1M, x2, N minus M with modulo of N. This is basically x1N convoluted with x2. So this is how it is proved. Let's once go through it very quickly once again, so that if you have missed somewhere, you can understand it. So in this one, what we are doing is we are doing the, we are taking the convolution in the time domain, which will result in multiplication in the frequency domain. But while proving, we started with the RHS. While proving, we started with the RHS. So RHS we have taken. So we took the IDFT of the RHS. RHS was given as x1k into x2k. So I took the IDFT, inverse DFT of this one. When you take the inverse DFT, you will just firstly write the formula of inverse DFT. This full thing you will take as 1, means as a one single unit, and then you wrote the formula here. After that, you wrote the DFT of this one and this one individually. Then next what we did was, we are doing smartly, we are trying to make the groups. So how to make the groups here? First of all, we have to just change, because everywhere n equals to 0 to n minus 1 you cannot keep it, because these are two different signals. So here we put m, here we put p. Thereafter, what we did was, now this x1, x1m and x2p, if you take it outside and just put the e to the power minus things together, then this is very, very important part. You have to, the whole red part is very, very important. E to the power minus j 2 pi k n, m plus p minus n. Now we just changing it to plus. If you write n minus m minus p, see, n is basically my signal x1 and x2n. So I am just taking this as the base and then writing in this manner. In this manner, it was not easily comprehensible. So it is better to write in this manner so that you can understand that n minus m minus p means shifting from n. Now this n minus m minus p is taken as an integral multiple of capital N. So I am writing it qn. Now this capital N and this capital N gets cancelled. When you put n minus m minus p is equal to qn, these two gets cancelled. You only have e to the power j 2 pi q into 2 pi q into k. So since k is changing from 0 to n minus 1, we wrote it in this manner. Now this whole thing is 1, since q is an integer. You know, it is cos 2 pi plus cos 2 pi q plus j sine 2 pi q. So since q is an integer, this is always going to be 1. Now 1 raised to the power of k will be equal to n, because here it is summation from 0 to n minus 1. So you are adding 1 n times. So that's why the answer is n. Then we are taking this n and putting it in this part. We have calculated what? We have calculated for this part. For this whole part, the value has come. For this whole part, the value has come equal to capital N. So we wrote this capital N and cancelled it with this one. Thereafter, we are left with a very small thing. This P, you can write it as N minus M minus Qn. Why we are writing it in this manner? Because capital N and small n is already there. Means it is the part of our DFT. So only M is left. So that M is just for shifting. This one is just for shifting. So once you write it this way, it will come in your mind that basically this is, since we are doing circular convolution, it is modulo n. So shifting is with modulo n over here, and n minus m modulo n. Then both the things, and also we are writing this in this manner so that both the places you have m as the variable, m equals to 0 to n minus 1, m equals to 0 to n minus 1. After that, you wrote it this way, and this, then you can finally identify it as circular convolution. This is it. Thank you, everyone. The next class will be doing circular correlation and Parseval's relation.